Hello everyone, and welcome back to RustPlanet. Today we are diving deep into cache implementation considerations with AWS Elasticache and Redis. In previous tutorial, we conquered the basics of setting up Redis server on AWS and interacting with it using the Rust code. This time we are pushing the limits, exploring advanced caching strategies that will turn your app into a sweet daemon. Get ready to unlock the mysteries of different caching implementation. We'll compare and contrast various approaches to figure out the perfect fit for your needs. Ensure data consistency across your cache and database with clear hands-on Rust code demonstrations. Catch evictions and TTL. Learn how to manage your cache efficiently, preventing outdated data from slowing you down. Whether you're a seasoned developer or just starting your caching journey, this tutorial has something for you. I'll break down complex concepts into easy to understand steps, complete with practical Rust code examples. So buckle up, hit that subscribe button, and let's unlock the full potential of AWS Elasticache and Redis together. Don't forget to leave the comment below with any questions or caching challenges you're facing. I'm here to help. If you haven't seen my previous video on setting up AWS Elasticache and Redis, check it out. It will provide a solid foundation for today's deep dive. Alright, let's get started. So, is it safe to cache data? In general, yes, but sometimes your data might be out of date, and so you may have eventually consistency. So it's not for every type of data sets. Okay. Some data you want to make sure that you only cache it if it's okay to cache it. Is caching effective for data? Is also another question you need to ask yourself. So for example, if your data is changing slowly and few keys are frequently needed, then that could be great. But for an anti-pattern, for example, if data is changing very quickly and you need all the key space in your data set, then maybe caching will not be as effective. Then you need to ask yourself the question, is the data structured correctly for caching? For example, if you have key value or if you want to store your aggregation results, caching is great. But you need to make sure that data is structured accordingly before caching it. Because caching is about saving time. It's about optimizing. It's about getting there faster. So you want to make sure that the data is structured the correct way for your queries. And then final question, which is the more important one. Which caching design pattern is going to be most appropriate for us? And this discussion we are going to have right now. So there is the first one called lazy loading, cache aside or lazy population. The three things mean the same thing. So let's have a look. So we have our application, we have Amazon Elasticache, Amazon RDS, and there are three distinct components. So if our application goes and wants to read something, first it's going to ask the cache. And so Elasticache, it would be Redis or memcached, would say yes, I have something, and it's called a cache hit. That's the greatest case. Now if there is no cache hit, then it's called a cache miss. So the application makes a request to Elasticache. Elasticache doesn't have the data, so we get a cache miss. So we need to be able to find the data where is. So we go and read the data from the database. In this example, Amazon RDS. Then the application has correct data. And what it's going to do is that it's going to write the data to the cache to make sure that any other application who requests the same data will go directly into cache hit. So this architecture is great because only the requested data is going to be cached. If there is no data that is requested from RDS, it will not end up in the cache. It's very efficient. And in case somehow your cache gets wiped out or you have a node failure, then it's not fatal. It will increase latency because the case needs to be one warm. By warm means all the reads have to go to RDS and then be cached. So that's what the warm up is called. But there are some cons. First of all, if we get a cache hit, it's great. But if we get a cache miss, that means there are three network calls being done from our application to Elasticache, which is a cache miss from our application to RDS, which is read from database, and finally another write to cache. And so far, for your users, when they're reading something and they see some latency, they're not used to it. And so that three round trips may be a bad user experience. And finally, stale data. So if your data is updated in RDS, then it will not be necessarily updating in Elasticache. So it's possible to have outdated data in the cache. And that's what you need to ask yourself. Is my data okay to be out of date and eventually consistent? So that's the first case. So now let's take a look at an example of lazy loading in Rust. Extern create Redis. This line imports Redis crate, which provides tools for interacting with Redis, a popular in-memory data store. Use Redis commands. This line brings the command straight into the scope, allowing the code to use various Redis commands within this module. Use Serde deserialize serialize. This line imports deserialize and serialize traits from the Serde crate, which are used to convert the data between Rust structures and formats like JSON. Next, use SQL. This line imports multiple features from SQL Crate, which is a Rust SQL toolkit for working with databases. Next, we import the .env crate, which allows loading environment variables from .env file. Next, we have Tokyo main. This attribute marks the main function as asynchronous, enabling it to use features from Tokyo runtime for concurrent operations. Async function main is the entry point of our program. Next, .env.ok. This line attempts to load the variables from .env file located in the project's root directory. If the file exists and is valid, its contents are loaded into the environment. If the file does not exist, there is an error. The OK method gracefully handles it by calling none. Next, constant db URL. This line declares a constant named db URL that stores the database connection string. It specifies that the database is an SQLite database located in the file named user.db. Next, we have a if statement which checks if the database file at the specified URL exists using SQL database exists function. This call is asynchronous and it awaits completion. If the database does not exist, the code within the block executes. Otherwise, the code in the else block will execute. In the if block, we have a match statement SQLite create database. This line attempts to create database at the specified URL using SQLite create database function. It is also asynchronous and awaits completion. The match expression handles the outcome of the database creation using OK. If the database is successful and a success message is printed. If it's an error, then the program panics with an error message. Now let DB. This line tries to connect to the existing database using SQLite pool options new function. It configures a connection pool with maximum of 10 connections that attempt to connect using the specified URL. The result is stored in a variable named db. If the connection is successful, a success message is printed and the connection pool is used in the subsequent database operations. If an error occurs, an error message is printed with the details about the error and the program exits with the error code 1. Next, we have let result SQL query create table if not exists users with ID integer, which is primary key and which is not null, name, which is of type varchar of 250 characters, which is not null, dot execute. This line executes an SQL query that creates users table if it does not already exist. It uses the SQL query function to build a query and the execute method to run it against the database connection. The await keyword awaits for the synchronous operation to complete. The unwrap method is used to extract the result. Number of rows affected assuming the operation was successful. However, it is generally recommended to handle potential errors more gracefully instead of using unwrap. Next, we are printing the result of the table creation query. Let user result is equals to query as insert into users ID name values, returning ID name, bind 1 and bind pawn. Here this complex line inserts a new user with ID 1 and name pawn into the users table and retrieves the inserted user details. Let's break it down. The query as is a part that builds a SQL query using query as function that specifies that the resulting data should be mapped to user struct. Next, we have insert the string insert into users, which is the SQL query. This is the actual SQL query string for inserting user. The question mark placeholder will be replaced with the values found later. Next, the dot bind. This part binds the value 1 to the first question mark placeholder in the query representing the user ID. Next we have dot bind pawn to string. This part binds the string pawn to the second placeholder representing the username. Next we have fetch one, and we pass in the reference to the DB, and we await. This part executes the query against the database and fetches first row as user struct. The await keyword waits for the synchronous operation to complete. Next we match on the user result. If the insertion is successful, the inserted user details are stored in the user variable, which is of type user struct. Next we print the success message with the created user details. If an error occurs, an error message is printed with the details about the error, and the program executes with the error code 1. This line retrieves the Redis connection URL from the environment variable Redis connection URL. It assumes that this variable is set, and if it is not found, the program panics with an error message. Next we have let mute Redis client open Redis connection URL dot unwrap. This line attempts to open a connection to Redis server using retrieved URL. The unwrap method extracts the client object if successful, otherwise it panics with an error message. Next we check the cache. This line tries to retrieve the user data with the ID 1 from the Redis cache using get method. This specifies the key type I32 for ID and the value type string for the name. If the user data is found in the cache, it's stored in the serialized user variable as JSON string. Let user Saturday JSON from string. This line deserializes the JSON string into the user using the Saturday JSON from string function. The unwrap method assumes that successful deserialization, but consider handling potential errors more gracefully. This line prints the retrieved user details from the cache. If the user is not found in the cache error, the code within the error block will execute. Here we retrieve user from the SQLite if it is not found in the cache. Let user result query as user select ID name from users where ID bind one fetch one passing reference db.await. This line retrieves the user with ID 1 from the SQLite database if it wasn't found in that cache. It uses SQL X query function to build the query, binds the ID 1, fetches the first row as the user struct, and waits for the completion with await. If the user is found in the database, the retrieved user details are stored in the user variable. Next, we serialize the user variable using Saturday JSON toString. Next, we populate the cache. Let client set ID 1 and serialized user. This line stores the serialized user back into the Redis cache with key ID 1. The unwrap method assumes successful storage, but consider potential errors more gracefully. The underscore indicates that the return value is not directly used. In case of an error, if the user is not found in the database, we print user with ID is not found. Here we are defining the user struct. This line defines the user struct that represents user with ID name fields. The derive macro automatically implements several useful traits for the struct. Clone allows creating copies of the struct. From row enables converting database rows into user structs using SQLX. Debug provides human readable representation of the struct for debugging. Serialize enables converting the struct into JSON format. Deserialize enables converting JSON back into the user struct using Saturday JSON. Now let's run the code using command cargo run -bin lazy loading. Here you can see the output. Type of strategy is called write through, and write through is when you add or update cache when your database is updated. So let's have a look. Same thing, application Elasticache and RDS. And when your application talks to Elasticache, we get a cache hit, which is great. And when there is a write happening to RDS, so when our application modifies the Amazon RDS database, then on top of it, it's going to write to the cache. So this is why it's called write through, because we write through Elasticache to RDS. So what do we get out of this architecture? Well, the data in the cache is never stale. Okay, whenever there is a change in RDS, then automatically there will be a change in your cache. and this time you get a write penalty versus a read penalty. So before, when we had cache miss, we had to do 3 network calls in total, and that was a read penalty. But now when we write to the database, we have a write penalty. Each write now requires 2 calls, one to the database and one to the cache. And from the user perspective, a user is expecting more a write to take longer than a read. For example, if you are on a social media and you post something, then you expect the post to last maybe a 2 seconds. But if you fetch a profile, you expect to take a split second. So here the users understand that any write, any changes to the database may take a little bit longer. So there may be better from user perspective. Now, what about cons? Well, there is missing data. Until Amazon RDS database is updated or added, that means that your Elastic cache or your cache in general will not have all the data it needs until the data is returned to RDS. So there may be a problem. And so for this, you can combine write through strategy with lazy loading. If your application does not find the data in Elastic cache, then it also does lazy loading into RDS. And so we can combine the two strategies together. And there we get the cache churn. This means that as we add a lot and lot of data in RDS, there will be a lot and lot of data in Elasticache. But there is a chance that this data will never be read. So that could be a problem. If your cache is very small, it is okay. Now let's take a look at an example of write through in Rust. First, extend create Redis. This line imports Redis crate, enabling the program to interact with Redis, popular in-memory data store. Next, we have Redis commands. This line brings the command straight into the scope, giving us access to various Redis commands. Next, we have use deserialize serialize. This line imports the deserialize and serialize traits from the Serde crate, which are used to convert data between Rust structures and formats like JSON. This is essential for storing and retrieving user data efficiently. Next, we have use SQL. This line imports multiple features from the SQL crate, which is a Rust SQL toolkit for working with databases. It provides a flexible and easy to use API for database interactions. Next, we have use.env. This line imports the .env crate, allowing us to load the environment variables from a .env file. This is especially useful for storing sensitive information like database credentials securely, avoiding the need to hard code them into the code. Next, we have Tokyo main attribute. This attribute marks the main function as asynchronous, enabling it to use the features from the Tokyo runtime for concurrent operations. This is particularly useful when dealing with asynchronous tasks like database interactions and Redis communication. Next, we have async function main. This line defines asynchronous main function, which is the entry point of your program. The async keyword indicates that the function can be suspended and resume execution as needed, allowing it to wait for asynchronous operations to complete without blocking. Next, we have .env OK. This line attempts to load environment variables from .env file located in the project's root directory. If the file exists and is valid, its contents are loaded into the environment. If the file does not exist or there is an error, the OK method is gradually handles it by calling none. This is the best practice for managing sensitive information securely. Next, we have constant variable called db_url. This line declares a constant named db_url that stores the database connection string. It specifies that the database is an SQLite database located in a file named user.db. This defines the location and type of database you are interacting with. Next, we have an if condition. This if statement checks if the database file at the specified URL exists using SQLite database exists function. This call is asynchronous and awaits for completion. If database does not exist, the code within the block executes and creates it using SQLite create database method. Next, let DB match SQLite options new. This line tries to connect to the existing database using SQLite options new function. It configures connection pool with maximum of 10 connections and attempts to connect using specified URL. The result is stored in the DB variable. Next, let Redis connection URL standard environment variable Redis connection URL.accept. This line retrieves the Redis connection string from the environment variables. If it's not found, the program panics with the error message. Next, let mute client open Redis URL connection.unwrap. This line attempts to open a connection to Redis server using retrieved URL. The unwrap method extracts the client object if successful, otherwise it panics with an error message. This line executes an SQLite query that creates an user's table if the table does not exist. It uses SQL query function to build the query and execute the method to run it against the database connection DB. The await keyword awaits for the synchronous operation to complete. The unwrap method is used here to extract the result. Number of rows affected, assuming the connection was successful. However, it's generally recommended to handle the potential errors more gracefully instead of using unwrap. This complex line inserts a new user with ID 1 and name pawn into user's table and retrieves the inserted user details. Let's break it down. Query as this part builds an SQL query using query as function and specifies that the result data should be mapped to a user struct. This creates an efficient way to map database rows to structs. Next, we have the string insert into users ID, name, values with placeholders returning ID and name. This is an actual SQL query string for inserting users. The question mark placeholders will be replaced with the values bound later. Dot bound 1. This part binds the value 1 to the first placeholder in the query representing the user ID. This sets the ID value for new user. Second placeholder representing the username. This sets the name value for the new user. Next, we call the method fetch1 passing a reference to db.await. This part executes the query against the database and fetches the first row as user. Struct. The await keyword awaits for the asynchronous operation to complete. This retrieves the newly inserted user details. Next, we match an user result. Let serialized user is equals to JSON to string passing the reference of user. This line serializes the user struct into JSON string using JSON to string. The unwrap method assumes successful serialization. Next, we populate the cache. This line stores the serialized user data back into the Redis cache with key 1. The unwrap method assumes a successful storage, but consider handling potential errors more gracefully. The underscore indicates that the return value is not directly used. This populates the cache with newly inserted user data. Next, we print the success message that the user is created. Next, this print line prints a success message with the created user details, providing the feedback on the operations outcome. Next, we check the cache. This line tries to retrieve user data with the ID 1 from the Redis cache using get method. It specifies the key type i32 and the value type string. This attempts to retrieve the user data from cache if it was previously stored. If the user data is found in the cache, it is stored in the serialized user variable as JSON string. Let user is equals to JSON from string. This line deserializes the JSON string into user struct using this method. Next, this line prints the retrieved user's details from the cache, highlighting the efficiency of using cache for frequently accessed data. Next, we retrieve the user from the database if it does not exist in the cache. Next, we match on the user result. If the user is found in the database, it is serialized and stored in the cache. If it's an error, we say we print unable to find the user with the specified ID. Here, this line defines user struct using derive macro to automatically implement several useful traits. Clone allows creating copies of the struct. From row enables converting database rows into user structs using SQLX. Debug provides a human-readable representation of the struct using for debugging. Serialize enables converting the struct into JSON format using JSON. Deserialize enables converting JSON data back into user struct using JSON. The struct has two fields, ID and an I64 integer representing user's unique identifier, name, a string containing user's name. Now let's run the code using the command cargo run pin right through. Here you can see the output. We're able to get the user from the cache. Then there is a cache evictions and time to live or TTL. So your cache has limited size, and so there can be something called cache eviction to remove data out of your cache. So for example, it can happen if you delete an item explicitly from the cache, or if the memory of the cache is full and then your item has not been used recently and therefore it is going to be evicted. It is called LRU for least recently used. Or so we set an item time to live or TTL, which is saying, hey, you can live for only 5 minutes, and in 5 minutes I want to cache evict you. And then TTL is very helpful for really any kind of data, would it be leaderboards, comments, activity streams, etc. And depending on your application, your TTL can range from a few seconds, so this is a very short TTL, to hours or days. But even a TTL of a few seconds for some data that is very requested can be extremely effective for a cache. So TTL is great strategy to keep a balance between having data stay in the cache and also being evicted, so that new data takes place and replaces it. So if somehow you have too many evictions though, because your case is always at full memory, then you should consider updating your cache size by scaling up or out. So that means making your cache bigger. Thanks for watching. Happy coding.